It's just a matter of weeks before the unique interstellar comet known as 3I Atlas is expected to pass closest to the sun.
Now, until recently, we haven't seen dust being pushed back behind the object by the solar radiation pressure.
When astronomers first noticed 3I/Atlas streaking across the skies, its discovery was met with excitement because it represented only the third recognized interstellar object to pass through our solar system. The excitement quickly turned into something far more dramatic when research teams at NASA and Harvard announced that the trajectory of this rare visitor could end with it plunging directly into the sun. For scientists, this possibility is not simply a spectacle of destruction, it is a chance to study in real time how interstellar objects interact with a star, what secrets they carry from distant star systems, and how their fates inform our understanding of cosmic dynamics. Before we start, smash the like and subscribe buttons for more updates. The journey of 3I/Atlas is unlike that of any comet or asteroid native to our solar system. It originated far beyond the Oort cloud, carrying with it the chemical and structural fingerprints of an alien environment. As it entered the region dominated by the sun's gravity, its hyperbolic orbit confirmed it was no ordinary solar system object. NASA and Harvard researchers focused on tracking its velocity and refining its path with the most precise observations available, noting that gravitational tugs from the sun and planets could bend its course toward a terminal fall into our star's inferno. This possibility brings with it an extraordinary opportunity to witness an interstellar body meet its end in our cosmic backyard. The implications of such an encounter are vast. For one, it would offer astronomers a front-row seat to study how the sun vaporizes material never before exposed to its radiation. Comets and asteroids that circle our star are well understood in terms of sublimation and disintegration. But 3I/Atlas is thought to contain exotic ices, complex compounds, and mineral formations foreign to our solar system. As it nears the sun, instruments across observatories and spacecraft will be watching for outgassing, fragmentation, and the spectral signatures of rare elements. The sun, in essence, becomes a natural laboratory furnace, burning away the layers of this interstellar messenger and revealing its true nature piece by piece. Harvard's astrophysics teams have emphasized that the fall of 3I/Atlas into the sun would be more than just a curiosity. It could provide one of the clearest data sets ever gathered about interstellar chemistry. By examining the light signatures as the object disintegrates, scientists might detect compounds that hint at processes occurring in distant star systems. Imagine finding molecular fingerprints that tell of conditions around other suns, organic compounds, exotic silicates, or volatile ices formed under alien radiation environments. Such findings could reshape theories about planet formation elsewhere in the galaxy. NASA, too, has a keen interest in the dynamics leading up to this potential collision. The sun is not just a backdrop, it is a complex, active star with an ever-shifting corona and solar wind. As 3I/Atlas descends into this turbulent atmosphere, it will interact with magnetic fields, charged particles, and extreme radiation. Observations could reveal how interstellar dust and gas respond to solar storms, flares, and the intense pull of gravity at close range. Each moment of this descent is a test case in astrophysical modeling, improving predictions not just for interstellar objects, but also for comets and asteroids that venture close to stars in general. Another striking implication lies in what the event says about the sheer randomness and interconnectedness of the cosmos. Interstellar space is unimaginably vast, yet here we are, with a body from an entirely different system on a path to annihilation within our sun. It raises questions about how many such objects pass unnoticed, how often they might be captured or destroyed, and what role they play in seeding new environments with alien materials. If interstellar objects regularly deliver compounds into solar systems, they could play a quiet but profound role in spreading the building blocks of complexity across the galaxy. The potential solar impact also underscores the sophistication of modern astronomical tracking. Detecting 3I/Atlas in the first place was already a challenge, given its faint light and rapid movement. Projecting its path forward involves balancing gravitational influences, solar radiation pressure, and the unpredictable jets of gas and dust it releases. Harvard's involvement ensures a high level of theoretical analysis, with teams running simulations on supercomputers to anticipate every possible trajectory. NASA brings the observational power of spacecraft and Earth-based telescopes, refining predictions with each passing day. Together, the collaboration highlights the marriage of theory and observation that defines modern astrophysics. For the general public, the story of 3I/Atlas is also a window into the drama of cosmic events. Few things capture the imagination like the notion of a wanderer from another star system plunging into our own sun. It feels like a collision of two worlds, or rather, of two stellar neighborhoods. The sun, though massive beyond comprehension, will barely notice the event in terms of physical change. Yet for human observers, it represents a moment where distant and local cosmos meet in a fiery display. It reminds us of the transient beauty of the universe, where even colossal objects can end in mere seconds under the weight of stellar forces. Scientists are especially focused on timing and monitoring the lead-up to the event. As 3I/Atlas draws nearer, its brightness will fluctuate. Jets of gas will create a temporary atmosphere and tail, making it a target for both professional and amateur astronomers. Telescopes tuned to infrared, ultraviolet, and visible light will attempt to capture every stage of heating, cracking, and breaking apart. Instruments designed for solar observation, such as NASA's Solar Dynamics Observatory, may catch glimpses of the object as it enters the corona. For a brief period, humanity will watch an interstellar object dissolve into a star, and the data collected could fuel decades of analysis. There is also a broader theoretical significance to consider. If interstellar objects like 3I/Atlas can be drawn into stars relatively often, then stellar systems may play a major role in recycling cosmic material. Alien rocks and ices are not just passing through, some are consumed, adding trace elements to the chemical makeup of stars. This cycle could be an underappreciated part of galactic evolution. Harvard's teams are particularly interested in whether these processes influence stellar composition over long timescales, subtly altering the balance of elements in ways that may affect star lifespans or even planetary system development. Beyond the direct science, there is the symbolic power of the event. Humanity is watching with advanced instruments an interstellar traveler come to its end. That perspective of seeing across both time and space is itself an achievement. Just a century ago, the very notion of tracking such an object would have been impossible. Now, not only can astronomers find it, but they can also predict its fate with remarkable accuracy, set up campaigns to watch it unfold, and extract information that may answer fundamental questions about life, chemistry, and cosmic origins. The attention this potential impact garners also reaffirms the importance of interstellar astronomy as a frontier. Objects like Oumuamua, 2I/Borisov, and now 3I/Atlas are not rare anomalies. They may be common, yet our technology is only just catching up to detect them. Each one brings a story from another corner of the galaxy, carrying within its mass a record of environments far beyond our own. Watching one disintegrate in the sun is dramatic, but equally important is the reminder that there are countless others waiting to be found, studied, and perhaps even visited in the future. The sheer physics of the potential plunge is also captivating. As 3I/Atlas approaches perihelion, the point of closest approach to the sun, it will be moving at extraordinary speeds. Its kinetic energy will convert into light and heat as it breaks apart, producing a flare that, if large enough, may even be detectable in solar monitoring instruments. The spectacle will not rival a solar flare in intensity, but its uniqueness lies in the fact that it is an alien visitor, destroyed in our own star's furnace. For scientists, the timing, light curve, and thermal signatures will all serve as valuable data points in understanding high-energy destruction of solid bodies. NASA's planetary defense offices are not directly involved, since 3I/Atlas poses no threat to Earth. However, the tracking techniques developed for monitoring potentially hazardous asteroids are being put to use here as well. Precision in orbital calculations is vital, not just for academic curiosity, but also for refining the overall models that protect our planet. This means that even as 3I/Atlas heads toward destruction, it contributes indirectly to Earth's safety by sharpening the tools used to track other objects. The synergy between curiosity-driven science and practical defense is one of the more subtle implications of the event. Public fascination is bound to grow as the story develops. The idea of a cosmic traveler plunging into the sun taps into both fear and wonder, echoing myths of Icarus flying too close to the star. Modern science strips away the myth but replaces it with something even more profound: the real observable drama of matter from another solar system being annihilated before our eyes. News coverage, educational programs, and live observatory feeds are likely to turn this into a shared experience, one that blends rigorous science with awe. The broader astronomical community is preparing to make the most of this opportunity. International collaborations are being organized, data sharing agreements are in place, and observatories around the globe are adjusting their schedules to keep eyes on the interstellar visitor. The sun itself, normally too bright to observe directly except with specialized equipment, will become the stage for this rare performance. Instruments tuned to pick up faint changes will be straining to record the faint glow of a disintegrating object against the overwhelming brilliance of a star. Every photon captured could tell a story about chemistry, structure, and cosmic history. As the countdown progresses, anticipation will build. Each new observation refines the orbit, narrowing the likelihood of a solar impact. Each spectral analysis adds detail to the object's composition. Each simulation run by Harvard's astrophysicists enhances understanding of what will happen during the final moments. Even if the object ultimately veers away from a direct plunge, the journey itself is rich with discoveries. But if the predictions hold true, humanity is on the brink of watching something that has traveled light years meet its fiery conclusion just a few million miles away from Earth. The event also challenges our sense of scale. The Sun, a star so massive that over 1 million Earths could fit inside it, will swallow 3I/Atlas without a trace. Yet for us, that trace is everything, an opportunity to learn, to expand horizons, to marvel at cosmic coincidences. In a way, the fate of 3I/Atlas mirrors the fate of many things in the universe: to shine briefly, to carry stories across space, and finally to return to the fires from which all matter once came. At every level, scientific, symbolic, and emotional, the possibility of 3I/Atlas colliding with the sun represents one of the most remarkable celestial events of our time. It is not simply about watching a rock burn. It is about connecting with the cosmos, about glimpsing processes that shape galaxies, about seizing rare opportunities to expand knowledge. NASA and Harvard's announcement has set the stage, and now the world waits, instruments ready, for the moment when an interstellar wanderer meets the star that anchors our solar system. The revelation that 3I/Atlas may soon meet its end in the sun has ignited an unprecedented wave of curiosity, speculation, and scientific planning. What makes this moment truly historic is not simply the possibility of another interstellar object visiting our solar system, but the fact that its trajectory appears to place it on a collision course with our star. The sun is often treated as a constant backdrop to the unfolding drama of planetary orbits. Yet here, it becomes an active participant in the cosmic stage. An interstellar object, born in another stellar nursery, wandering for millions of years through galactic space, is now potentially destined to be consumed by our own star. This scenario provides layers of insight into astrophysics, planetary science, solar dynamics, and even questions about the origins of matter itself. One of the most striking aspects of this event lies in how it bridges cosmic scales of time and space. Interstellar objects like 3I/Atlas are thought to have been ejected from other planetary systems during their chaotic youth. Planet formation often involves gravitational scattering, where giant planets or dense stellar clusters fling smaller icy and rocky bodies into interstellar space. Most of these objects wander forever in the cold void between stars, but a few happen to stumble into foreign systems. For 3I/Atlas, the incredible odds of entering our solar system and then being drawn into the immense gravitational well of the sun highlight the interconnected nature of the galaxy. What began as a small piece of debris from a distant star-forming region is now part of a story that unfolds under the gaze of humanity's telescopes. The possibility of impact with the sun is a moment where theory and observation converge. Researchers from NASA and Harvard are leveraging both ground-based facilities and space observatories to model the physical processes that will occur. This is not merely a matter of predicting a fiery end. It is an experiment in understanding energy transfer on a cosmic scale. As 3I/Atlas approaches the Sun, it will face temperatures high enough to vaporize nearly every known element. This offers scientists a unique opportunity to test models of sublimation, thermal cracking, and plasma interactions. The Sun's radiation will peel away layers of volatile ices and expose the deeper rocky core if one exists. Each stage of this process can be studied with spectroscopic instruments that record the wavelengths of light emitted by the dissolving body. For planetary scientists, this is akin to dissecting an alien sample without ever touching it. Another dimension of significance arises from the Sun's own behavior. The solar corona, the outermost layer of the Sun's atmosphere, is a turbulent, magnetically charged environment. It is hotter than the Sun's surface, a paradox that scientists still seek to fully understand. Into this environment, 3I/Atlas may plunge, interacting with charged particles and magnetic fields in ways that have never been directly observed. NASA's Solar and Heliospheric Observatory, along with other solar missions like the Parker Solar Probe, are uniquely positioned to capture this encounter. These spacecraft were designed to study solar winds, flares, and coronal mass ejections, but they could also record the first detailed instance of an interstellar object engaging with stellar plasma. This means that the event could simultaneously advance knowledge of interstellar chemistry and solar physics. Harvard's theoretical astrophysicists are particularly excited about the chance to model these dynamics. The interplay between gravitational acceleration, solar radiation pressure, and the unpredictable eruptions of solar activity makes the fate of 3I/Atlas a complex equation. Every moment leading up to its demise can inform equations about orbital dynamics under extreme conditions. When gravitational forces pull an object to incredible velocities, relativistic effects and complex resonance patterns emerge. Capturing these dynamics provides an experimental counterpart to long-standing theoretical predictions. For instance, the acceleration experienced by the object near the solar surface could offer comparisons to other high-gravity environments in the universe, such as those near compact stars. The scale of the plunge cannot be overstated. As 3I/Atlas accelerates toward the Sun, it will reach velocities that dwarf any spacecraft humanity has ever launched. Its kinetic energy will be staggering, even though it is tiny compared to the Sun itself. The conversion of that kinetic energy into heat, light, and plasma emissions will produce a distinctive signal. Solar instruments that continuously monitor for solar flares could pick up this unusual burst of radiation, distinguishing it from typical solar activity. If detected, it would provide an unmistakable fingerprint of an alien object's destruction, a cosmic signature of matter that has journeyed across the void being erased in a star's atmosphere. The collision potential also brings philosophical implications. Humanity has always wondered about the origins of life, matter, and the cosmic pathways that bring elements together. Interstellar objects are messengers from other stars. They carry within them not just atoms, but histories of processes that unfolded under different stellar radiation, in different chemical soups, and within different planetary systems. To watch one disintegrate in our Sun is to witness the merging of two stellar legacies: the Sun's ongoing cycle of energy and the alien history encoded in 3I/Atlas. Even as the object is annihilated, its final moments reveal those hidden stories. The plasma emissions it releases will become part of the Sun's corona, meaning that material from another star system will literally be absorbed into our own star. The scientific community is also treating this as an exercise in coordination and precision. Global networks of telescopes will monitor the lead-up, each specializing in a different wavelength. Radio observatories will listen for plasma interactions, while infrared telescopes will seek to detect the heat signatures of sublimating ices. Ultraviolet instruments can catch the flares of exotic molecules as they are broken apart. This multi-wavelength campaign reflects the maturity of modern astronomy, where collaboration across continents and disciplines ensures that no piece of data is missed. Harvard's role in computational modeling and NASA's expertise in observational missions create a partnership that exemplifies the international spirit of discovery. From an educational standpoint, The possible destruction of 3I/Atlas is a teaching moment of unprecedented scale. Students learning about physics, astronomy, or even philosophy of science can look to this event as a live demonstration of the principles they study in textbooks. Concepts like gravitational acceleration, heat transfer, molecular spectroscopy, and orbital mechanics will all come alive as the event unfolds. It is a rare instance where the universe itself provides a classroom, with the sun acting as a blackboard upon which the fate of an interstellar body is written in fire. One of the intriguing elements of this scenario lies in the unpredictability of outcomes. While models suggest a likely plunge into the sun, subtle shifts in trajectory could alter the final approach. Outgassing from the object, jets of vapor released as ices sublimate can act like miniature rocket engines, nudging it in unexpected ways. These perturbations are difficult to predict with precision, which means that scientists must track every change meticulously. Each adjustment in trajectory reveals more about the physical composition of the object. If the outgassing is strong, it suggests an icy, volatile-rich body. If it remains stable, it could point to a rockier, denser structure. Thus, even the path it takes en route to the sun is itself a source of discovery. The fate of 3I/Atlas also ties into a larger narrative about the movement of matter across the galaxy. Every star system ejects debris during its chaotic beginnings. Much of this material drifts endlessly, but some of it finds its way into new systems where it may collide with planets, moons, or stars. These interactions are part of the great recycling mechanism of the galaxy. A molecule formed near one star could eventually be absorbed by another. The galaxy is, in this sense, a shared pool of matter in which stars and systems exchange fragments of themselves over eons. The fall of 3I/Atlas into the sun is a local manifestation of this grand cosmic circulation. The technical achievements involved in predicting and observing this event cannot be overlooked. To locate a faint, fast-moving object from interstellar space is already a feat. To calculate its trajectory with enough confidence to suggest a solar impact demonstrates the precision of modern astronomy. Each calculation is based on data gathered from telescopes scanning the sky, analyzing faint points of light against the background of stars. Sophisticated algorithms process this data, correcting for atmospheric distortions and instrumental noise. These numbers then feed into models that project the orbit forward, taking into account the pull of planets, the push of radiation, and the subtle effects of mass loss. It is an astonishing orchestration of mathematics, physics, and engineering that makes such predictions possible. At the human level, there is a deep sense of wonder. To contemplate the journey of 3I/Atlas is to think about a piece of matter that has traveled for untold millennia through interstellar space, untouched by any star's warmth. Its surface has been frozen for eons, bombarded only by cosmic rays and interstellar particles. Now, suddenly, it is thrust into the blazing furnace of a star. That contrast between the deep freeze of interstellar space and the searing heat of the sun is almost poetic. It captures the extremes of the universe and our unique chance to witness a transition from one extreme to the other. The potential of 3I/Atlas to end its journey in the sun also serves as a preview of processes that occur across galaxies. Stars are constantly interacting with surrounding material. Some of it is drawn in, some expelled, some redistributed. What we see here in miniature may be a common event elsewhere. Interstellar debris being consumed by stars, contributing in small ways to their composition. By watching closely, we gain not just knowledge about this one object, but insight into a universal process. In this sense, the event is not just about our sun and this one object. It is about learning how stars and matter dance together throughout the galaxy. There is a cultural resonance as well. Humanity has long been captivated by the sun, worshipping it as a god in ancient civilizations, treating it as the symbol of light and life. To now watch as an alien object dives into it is to add a new chapter to that ancient fascination. The sun becomes both destroyer and revealer, annihilating 3I/Atlas but revealing secrets hidden for millions of years. This dual role echoes through mythology and science alike, blending the symbolic with the empirical in a way that touches both reason and imagination. In practical terms, the data gathered from this event could also inform future missions. As interest grows in sending spacecraft to intercept interstellar objects, understanding their compositions and behaviors becomes vital. If 3I/Atlas is indeed icy and volatile, it confirms that these bodies resemble comets. If it is rocky, it challenges assumptions. Either way, the knowledge will help engineers design instruments capable of surviving encounters with such objects. Observing the sun's destruction of 3I/Atlas is, in effect, a trial run, providing details that will shape humanity's first direct explorations of interstellar debris. The anticipation surrounding this event also highlights the importance of continued investment in astronomy. The ability to detect, track, and study objects like 3I/Atlas depends on advanced telescopes, international cooperation, and dedicated research. Events like these justify such investments by demonstrating the sheer value of knowledge gained. They also inspire the next generation of scientists, engineers, and thinkers who will carry the torch of discovery forward. Watching an interstellar object fall into the sun may ignite dreams of exploring beyond our solar system, of sending probes into interstellar space, or of building telescopes powerful enough to see similar objects far in advance. At the level of pure science, the possibility of a solar impact demands precise planning. Instruments must be aligned, data pipelines tested, and observation strategies coordinated. Every second of data counts, because the event itself will be fleeting. Once the object passes the critical threshold and begins to break apart, its destruction will be rapid. Observers must be ready, poised to capture spectra, images, and radiation signatures in real time. This urgency lends a sense of drama, turning what might have been an obscure astronomical footnote into one of the most highly anticipated events of modern astrophysics. There is the legacy of the event. Long after 3I/Atlas has been consumed by the sun, the data, images, and interpretations will remain. They will become part of the body of scientific literature, referenced by future generations as they build new theories and models. The name 3I/Atlas will carry with it the memory of a rare cosmic encounter, one that allowed humanity to glimpse across the gulf of space and time, to witness the end of an interstellar journey in the fire of our star. It is a reminder that the universe is not static but dynamic, alive with movements and interactions that sometimes intersect with our capacity to observe. The story of 3I/Atlas is thus not one of tragedy or loss, but of discovery and connection. Even as it disintegrates, it fulfills a role: to teach, to reveal, to inspire. Its plunge into the sun, should it occur, will not diminish its value. Rather, it will amplify it, turning destruction into revelation. For NASA, Harvard, and all those who watch, the event represents a cosmic gift, an unrepeatable performance staged by the universe itself. And for humanity as a whole, it is a reminder that we are part of this vast cosmos, observers and participants in a drama that stretches across stars. The anticipation surrounding 3I/Atlas grows with every new observation, because it is not just another astronomical curiosity. It is a lens through which many aspects of cosmic behavior can be examined simultaneously. What makes this case so unique is that it highlights how even the most familiar part of our existence, the sun, can become a stage for alien phenomena. Instead of studying the sun in isolation or speculating about the nature of interstellar objects in distant systems, humanity is about to witness a direct encounter between the two. The thought that matter from a star system unimaginably far away may be about to vanish in our own star creates a sense of immediacy and cosmic intimacy, as though the boundaries between stellar neighborhoods momentarily dissolve. One of the dimensions being emphasized by researchers is the question of scale. When people think of celestial collisions, they often imagine planet-sized bodies colliding in dramatic, catastrophic displays. Yet the interaction of 3I/Atlas with the sun demonstrates how even much smaller objects can yield enormous insight. The size of the interstellar traveler may be modest, likely comparable to a small comet or large asteroid, yet its significance far outweighs its dimensions. The moment it enters the sphere of the sun's destructive heat, it will unlock data that can shed light on interstellar matter, galactic migration of material, and the dynamic processes at play near stellar surfaces. Another area of intrigue lies in how interstellar objects differ from solar system bodies in their construction. For decades, planetary scientists have been cataloging comets, asteroids, and dwarf planets within our own system. These bodies, though diverse, generally fall into predictable categories shaped by conditions in the protoplanetary disk that formed our sun and planets. Interstellar objects, however, are formed under different initial conditions, different chemical balances, and often in the presence of other stars. This means that the moment 3I/Atlas begins to vaporize near the sun, its spectral emissions could display signatures unlike anything seen from native comets. It is here that the event becomes not just a spectacle, but a rare comparison tool, a way to contrast the birth conditions of our system with those of another. The importance of spectroscopy in this event cannot be overstated. Light emitted during the vaporization process is a treasure trove of information. By analyzing the absorption and emission lines produced, scientists can identify specific atoms and molecules, including exotic compounds rarely observed in our system. For example, if 3I/Atlas contains nitrogen-rich ices, complex carbon chains, or silicates that crystallized in unusual environments, the destruction process will make them visible. The sun's heat acts like a forced dissection, revealing internal layers as they boil off. Unlike a space mission, which might only scratch the surface of such an object, this event will expose its entire structure in sequence, layer by layer. In addition to chemistry, there is the question of dynamics. The interaction of 3I/Atlas with the sun's magnetic environment is something scientists are preparing to study with intensity. The sun's corona is filled with magnetic loops and charged particle flows, and any object plunging into this storm must interact in ways that generate turbulence. Observing how dust, gas, and plasma from 3I/Atlas behave within this context could teach researchers much about solar activity itself. The sun's corona has long been a source of mystery, particularly why it is so much hotter than the surface below. Watching the dissolution of a foreign body in this environment may offer a natural experiment to probe the corona's heating mechanisms. Another implication is related to the physics of fragmentation. As 3I/Atlas draws near the sun, tidal forces will pull at it, attempting to tear it apart before it even reaches the surface. Objects that pass too close to stars often break into smaller fragments, creating cascading clouds of dust and gas. This fragmentation process is difficult to model, as it involves both gravitational and thermal stresses interacting simultaneously. By recording the stages of breakup, scientists can improve models of how bodies behave under extreme stellar influence. This knowledge can later be applied to understanding the destruction of comets near stars, the breakup of exoplanetary debris, or even the accretion of material in disks around young stars. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I/Atlas possibly slamming into the sun? We want to hear from you. Thank you for watching, and see you next time.